Welcome to Calculus for the Biosciences. This is just going to be a little bit of review material and an introduction to the course of where you can find everything. So everything you will find in Blackboard. So you can just go to utsa.blackboard.com. That's where you'll find your textbook, the ebook. If you want an actual physical book, then you'd have to purchase it or borrow it from the library or rent it, one of those things. And you'll also find all the homework, which is within Wiley Plus. Also within Blackboard, I will post your group work. And this is what you will work on with your group on Fridays. It doesn't matter if you do it early, but I still want you to sit there and go over it with your group. Most groups don't even look at it until Fridays, which is fine because I give you plenty of time to work on it. Quizzes in class, random days, so always be prepared with a calculator every class. I highly doubt I'll give you a quiz that won't be on a Friday because typically I give it to you after you've worked on your group work. There will be a total of 3 tests, and then you'll have your final project with your group that you'll present on the final day of the exam. This is what the textbook looks like. You could use the 4th edition if you could find a cheaper one. So that's not a big deal. There's not a lot of changes. You want to get into Wiley Plus by simply going to www.wileyplus.com, and then you can set it all up in Blackboard. So what is calculus? Why do we need calculus? Nobody uses this stuff, right? Well, what you're going to notice as we go through this class is what you've been doing pretty much in all your math career, your regular math, is dealing with constant conditions, where we want to now look at changing conditions, which in this case you can see just by looking at this little dude in the car on the road, is that we're looking more at curves. And that's what we're getting to with calculus, where regular math problems have force, speed, and this is unchanging. In other words, it's constant. Where now when we get into calculus, we're actually going to see something changing. And that's one of the biggest differences in calculus. So as you can see, calculus is a pretty good topic, right? Because things change. You want to be able to work with any type of a problem that something is changing. In this class, what we're going to do, which is kind of weird, is when we get looking at different functions and curve functions, we're going to zoom way in to make it look linear. And because we know how to do lots of things already with linear functions, so that's what we're going to end up doing in this class. Well, who uses this stuff, right? Nobody. You can't even imagine anybody works with calculus every day. Well, I mean, this is used a whole lot. And in fact, it's kind of easy to convince people in the bio classes because they do a lot more applications with this, but with bacterial growth, blood pressure, cancer rates. I mean, think of all this that's listed here. These are things that are changing. Electric company, if they're looking at determining lengths between 2 towers, and you can see a curvature here. Kind of cool, some of the football stadiums now have where the rooftop opens, things like that. Business, want to be able to do well with your Apple, Apple computer, people like that to make better sales. Well, they need to be sensitive to the changes that are happening in demand. And of course, be able to say, well, demand is changing, going up, going down. What can we actually do? Automobile industry. There's kind of actually some pretty cool examples of the crash dummies, airbags, because that's something that's changing as the airbag is coming towards you. Forensic science, this seems to be a pretty new, popular area. It's not a new area, but a lot of people are going into it. And even musicians, way to approximate wave functions. You can detect tones on guitars, pianos, etc. And so certainly this stuff is used in many areas. It's just once you start to learn it, we kind of get into the theory a lot more in this class. And then you'll be able to take it to your next classes, physics, and say, oh, that's what we were doing in this class, and now I can actually apply it to something. So let's get into the material that technically you should already know, but maybe there's some things you don't remember. So some of this might be review for you. Some of this might be, yeah, I remember all that stuff. So when you dealt with linear equations, you knew linear meant a line. So you were looking at an equation of a line, and you had all the pieces where you could tell what the slope of the line was if you put it in the slope-intercept form, the y equals mx plus b, where m is the slope and b is the y-intercept. Have you ever wondered why they used m for slope? Or am I just the only weird person that thinks of things like this? M, slope, m, there's no, I don't know. If you actually look this up a little bit, you'll see that there are some people that think that it stood for the word modulus. And also you'll hear people say monter, because that means to climb, but that being the French word, but Descartes, who was French, never even used the letter M. So there's really no evidence why they use the letter M. They just say, it just happened. So there you go. If you're ever on Jeopardy and they ask you why they use M for slope of a line, it just happened. All right, so we're talking about linear equations, y equals mx plus b, where m is your slope, b is your y-intercept. And maybe you remember how to find the slope of a line. If you have 2 points, you take the rise over the run, or the change in y over the change in the x, or y2 minus y1 over x2 minus x1. You're going to see in this class, we're actually going to deal a lot with the slope. In fact, you're going to be doing a lot of things you already know how to do. We're just going to make it more mathy and make it look like you're doing something harder. So we're going to write it with these little delta, this Greek delta symbol, the change in y over the change in x. But guess what? That's still the slope. But we're going to make it look like this, so people will be like, oh, wow, you're learning that calculus stuff because they got weird Greek letters, and it'll make you look more intelligent, right? But guess what? You're still finding the slope. If you remember properties of slope, if you have a positive slope, then whatever it is, hopefully my bank account is increasing. If you have a negative slope, whatever it is, hopefully my weight is going down. If you have a zero slope, I hope you never do, because that's flat line, right? But this is something staying constant, that it's not changing. Okay, so these are the properties that you want to remember, because we get to a point where when we use these in a real world sense, we say something's increasing, decreasing, or constant. We don't typically say positive slope, negative slope. We want to know what that actually means. And then when you got through equations, you moved off into functions, because functions were a little bit more useful when you talk about inputs and outputs. You put something into it, you get something out. So we went from y equals to f of x was the only difference. And the big thing here was that we would talk about a domain, which would be your input. Most students just memorize its x values. And then we would have some type of a function relationship. So the function would do something. In this case, it takes 2 times the input and then adds 3. And it gives you a result, an output. And that's what we call, as far as a function, a range. Now, a lot of times you'll hear me call these independent variables and dependent variables. I kind of like this terminology because notice this 11 depended on what you put into the function. And as I mentioned earlier, we kind of change our format here. Instead of saying y equals x squared, now we say that we have a function of x, so my function name, my input is my x, and then after I input it, what I get is my output. Once you get to this level, there should be a lot of graphs that you just recognize right away. Meaning, if I say, what does a constant function look like? Okay, and you know that's just straight line, horizontal line. What does a linear function look like? Or in this case, the identity function. Remember the identity function, you could re-say this as y equals x. So any value that you put for x, it's going to be the same value for y. But again, also a linear function because the exponent on your x variable is 1. If we have x squared, most of you call that a parabola, quadratic function, x cubed, a cubic function. So all of these should be fairly familiar to you. Some of these might be, I kind of remember them. The square root function, as we know, you can't take the square root of a negative number, so that's why all my x's are positive. I have the cubed root function. That one might be like, kind of remember. Here, reciprocal function, or most of us call this the rational function. And then the absolute function, because when you absolute value, that your output's going to always stay positive. These piecewise functions kind of get left out. In fact, some instructors don't even talk about them. But they're important functions because they talk about things that are happening in pieces. And as you can see here, I have 3 different functions. I have a linear, that's what's happening right here. And in this case, I just have this one point. If x equals 1, then my f of x equals 2. And then I have this quadratic if x is greater than 1. And that's my x squared. You can kind of see the right side of the parabola happening there. These are important functions because you might have a function doing something, let's say, then we switch it off and it goes into just this mode here, and then we switch it back on. So I don't want you to ignore these types of functions because you are going to see them in this course, and so hopefully this is kind of a nice little refresher if you didn't get them too much in another class. So let's talk about how we can tell if a function is increasing or decreasing. It says a function f is increasing on an open interval I if for any choice of x1 and x2 and I with x1 less than x2, A lot of problems students have in a math class is they don't know how to read math. And that's not a knock against you, it's just hard, right? I mean, you got all these freaking symbols, and then there's words, and then there's letters and numbers, and so what you have to do, what I do, is draw a picture. So what this is saying, if you break it down, is you have 2 x values. You have an x1 and you have an x2. In this case, we're saying x1 is to the left is less than, so you can see this function's going up because at this point x1 is less than x2. Then if I go up to my actual function, I can see that the function value of f of x1 is less than x2. So all this is saying is we have some function, okay, it's increasing, it's on an open interval. Well, that's why these little circles are here. It's an open interval. If I pick any x1 and x2, I don't have to pick them here, I can pick them down here. As long as x1 is less than x2 in this interval, then it's telling us that my function values, f of x1, will be less than f of x2. And then, of course, the same thing, if you have a function is decreasing, again, you pick an x1 that's less than x2, but now your value of your function, f of x1, will be greater than f of x2. So kind of the key here is figuring out how to read. And like I said, the first thing I do is I pick up a pencil and start drawing. So a constant function, any choices that you pick of x1 and x2, any x's here, then the value of your function will always be equal. How do you deal with minimum and maximum of functions? How do you tell where a minimum and a maximum is? So a function, so we have some function here, has a local maximum at this value of c. So it's just some x value here that we're going to call c. If there is an open interval, so this is an open interval here, that contains this value of c, so that for all x not equal to c, so any other x's to the left of c, any other x's to the right of c, then this says f of x will always be less than or equal to f of c. So in other words, if I pick an x value right here, I'm to the left of c, but I'm less than it. If I pick it over here to the right, I'm still less than the value of that function. And that's what we call a local maximum of the function. Of course, the same thing occurs when you have a local minimum, but in this case, for all values you pick of x that does not equal c, the value of your function is going to be greater than. Okay, so and you can just kind of look at this, look at c and pick any other values here on the function, and you can see that they're always greater than, so that's where you have a local minimum. Transformations, these are things that are nice to have kind of in your arsenal. You might print this page out if you've forgotten a lot of this, but whenever you see a graph like x squared plus 3, that just means you picked up the x squared and moved it up vertically 3 units, then of course down. We have horizontal shifts, reflection about the x and the y axis, the vertical stretching and shrinking, as well as the horizontal. Again, not something that you may have all of these memorized. I think most students kind of have the vertical shifts probably the most, but as you start analyzing graphs in this class, and we'll even do some things where we hand draw graphs, it's kind of nice to remember these transformations. Composite functions. Now you're probably thinking, wow, she sure is reviewing a lot of algebra. You know what's funny in calculus? Well, not funny, but most of the students that struggle is because they don't remember their algebra. And maybe because it's been a while, because many of you have come straight out of pre-calculus. But one of the very, very important concepts that you learn in algebra is composite functions, where a composite function is simply a function within a function. And so if you can kind of get that down, you won't have any trouble with composite functions when we get to them. So if we have two functions, f and g are functions, then the composite functions, and a lot of students I hear them call this fog, f is composed with g is defined by this f of g of x. I kind of like it written like this on the right because it helps me remember how to do this, that I input in the inside, and then what I get, I input into the outside. And so that's kind of what this is saying here, is I input x into g, and then my g of x that I get, I input it into my f. I always think of one example, of a function within a function is, let's say you have a job, be nice, right? You got money, and you put part of your paycheck into an account that earns interest. So not only do you have one function that's figuring out how much your pay is going to be, right, by the number of hours, then you would have another function that you're putting it into this account that then would tell you how much you're earning in interest. Average rate of change. Every semester when I teach pre-cal, haven't taught it in a while, but I would tell students, this is very important. This is very important. You will see this again in calculus. Do they ever listen to me? No. It's towards the beginning of pre-cal, so I think that's why it's forgotten. If I'm looking at an average rate of change, so I have some value, c, and this is in the domain, so this is an x value, of some function, f of x, then the average rate of change of my function from c to another x is defined as the change in y over the change in x. Guess what? The average rate of change, that's the slope, right? We're just writing it differently, y2 minus y1 over x2 minus x1. We have two different x values, two different y values. We're saying they're not the same. And you'll also hear this called the difference quotient. So this is very important that you understand this concept that we're talking about an average. And we'll get into more of that. And so if I have what's called a secant line, So it says if I want to find the slope of the secant line, m, we said m is slope of a secant line, it's the average rate of change of a function equals the slope of the secant line containing 2 points on its graph. So in other words, what I just showed you, the average rate of change, is simply the slope of a secant line. Well, what's a secant line? A secant line is I have some function, okay, it's got curvy, kind of wavy here, and I pick any 2 points on that function and I connect the dots. That line that I connect the dots is what's called my secant line. If I find the slope of this secant line, what I'm doing is I'm finding the average between these two values. You can see I'm not finding an exact slope right here and an exact slope right here. I'm finding between these 2 points the overall average between those. And that's very, very, very important. So don't you dare forget it. So I always ask students, you know, what's in your past math classes, what's the one thing that just never made any sense to you? And they always say logarithms. Okay, I think most students kind of get exponentials, but in this class we are going to deal with logarithms and exponentials. So when we get to those areas, we'll kind of have some reminders about them, but for now, you need to remember some of these laws. So the laws of exponent. What's nice is that these are inverses of each other, meaning an exponent and a logarithm. So if you know one set of laws, then you know the other one. So if you're multiplying exponential functions and they have the same base, remember the base is the big one, so both of these have the same base, then you add the exponents. If you are multiplying inside parentheses to an exponent outside, then you simply multiply this exponent to the inside. Here you have to be careful that this exponent goes on both of these. 1 to any power is 1. This one kind of gets forgotten, and we'll use this a lot, is where you have a negative exponent is the same as writing 1 over same base, make the exponent positive. Now notice what happened here. Well, 1 to anything is still 1, so all I did was I brought my exponent outside, and then any base to the 0 equals 1. An exponential function is a function of this form where you have some base and your variable is the exponent. Okay, don't forget that. Sometimes students will get mixed up. They'll have like x to the second power and think that's exponent because there's an exponent, right? But exponential functions, your exponent is the variable. And just kind of a reminder of what the graphs look like. You can see the difference here is my base being 2 or my base being 1/2. But exponential functions are things that rise very quickly, okay, like diseases. And then of course something like decay could decay very quickly as well. Logarithm, again, so nice, is these are inverse of exponentials. So once you got one of them down, all a logarithm is an exponent. These are inverses of each other. So by looking at these, and this is what all this up here is saying, that if you have a one-to-one function, then you have an inverse. And if you remember with inverses, if you draw the line y equals x and it kind of separates them, or you can even say mirrors both sides, you can see that that's what's going on, then these are inverses of each other. So you can see here that if we have the a to the x, okay, function going on here, and my a is between 0 and 1, in other words, meaning that it's, as we saw in that last example, that it's a fraction, then I could write my logarithm, because it's the inverse, and it means the same thing. Okay, so in other words, you can see that these same values that we're saying that y equals whatever this exponential function is, and that's why we say a logarithm is being the equal sign, an exponent. Properties of logarithms. Again, some of these, as you're going to see on the next slide, they're the same as exponentials, but this is kind of a nice one to remember, that if you have a raised to the log, because remember this little a is the base, So what students kind of memorize is these cancel and you just end up with this. And the same thing's kind of going on here, but it's not in the actual exponent. What did we say if we had the same bases? What did you do with exponents? You added them. Well, guess what? That's what you do with logarithms. Same thing when you divide. When you divide exponents with the same base, you subtract them. Same thing with logs. In this case, we can bring this power out here to the front. And again, these are a lot of these properties you're going to see a lot in this course. So this is just kind of a reminder, like, oh yeah, I kind of remember we did that once. So kind of, you know, keep these sheets handy. So when you get to them, it's, you know, just second nature that you know how to split things up like this. Okay, mostly what we've talked about so far is you got in your algebra classes, right? And as I said before, students that struggle in calculus, they struggle with algebra. It's not the calculus. It's going back and remembering all the algebra. Well, there's also, we're going to start to move on to when you took pre-cal, your trig stuff. So you learned about circles, okay? You learned about, you have some fixed point here in the middle, and if I go around from any line that I make from that fixed point, that this is my radius. If I double it, meaning go to the other side, that's my diameter. I can write the standard form of an equation. Okay, so hopefully you kind of remember this. And in this case, the equation of the circle with my radius hk. And then this one here, when the origin was at 0, 0. So what's happening here is we're just plugging zeros in for h and k. And then this is my, if this equals 1, then we call that the unit circle. And then you took this with circles and you moved it into your pre-cal, okay, where you started learning trig. And what's the main thing you had to know to get through your trig class was the unit circle. Okay, so hopefully you kind of remember how to read these, meaning the sign. If I asked you what's the sine of 45 degrees, if you do degrees or radians, you remember the sine was the y value, the cosine was the x value. Also, you remember the tangent was sine over cosine. Once again, when we get working those type problems, I will remind you of this. But this is certainly good to just have on hand with you if you don't have, most students have a lot of, probably the top right quadrant 1 memorized, okay? And it's not a bad thing, you know, to have these memorized so you don't have to start searching for the sheet. So that is just an introduction. All of this information, hopefully you're like, yeah, I kind of remember that. I may not have been very good at it, but I do kind of remember it. And so when we get into actually using it, I will do a little reminder again. When we do logarithms, I'll say, remember, what do we know about logarithms? When we do something with a trig function, I'll say, oh, this is a cosine. What does cosine mean? And there'll be some identities, okay, that we'll have to remember. But I will try to remind you of these before we start getting really deep into them, because I realize there's all level of students that take this class. Some of you remember all of this stuff, and some of you, it's been a while, right? So see you in the classroom or online, and let's have a good class.